Hi, so my name is Stephen Henrie, and I'm the manager of application development over at Sony Computer Entertainment of America. And one of the things I wanted to discuss at this conference is something that I went through going through a project myself recently, evaluating some different technologies and what we came up with to use as a basis of an architecture. And it's kind of like a lightweight SOA framework, as you say, using Ruby, Apache Thrift, and AMQP. But before we get started, I knew that my talk here was right after lunch, so a lot of us are probably in a food coma or whatnot. So I wanted to make my graphics a little visually stimulating. And I also just wanted to let everybody know who Sony Computer Entertainment of America is, in case you just weren't sure. So hopefully this will wake everybody up.
Hello, world.
Dude, totally freaked me out. He scared the crap out of me, man.
So we are the PlayStation people. And as you can imagine, we have a pretty big week, some of you might know, coming up with our PlayStation 4 console coming out this week. So what I want to do is cover a little bit of background on what it is we do. So I manage a group of software developers, which we all use Ruby, and we work on internal applications that support the development and the hosting of the titles, and so of the game titles. And so this can be internal tools that manage the QA process, for example, where we get software or games from both internal Sony studios as well as external companies. To doing business intelligence, business mapping, data mapping, and also hosting. And so one of the things that I was tasked to do is, I'm fairly new to Ruby over the last year here, and one of my recent tasks has been to come up and work with some of the other hosting engineers to develop a new architecture for doing some cloud management software. The titles can be a little bit tricky, the games themselves, because they're not standard out-of-the-box applications, as you might imagine. So they have a lot of intricacies involved. And so I was evaluating with others some different technologies, and I just kind of wanted to share with the group here what some of those technologies were and what we ended up coming up with as the basis for what we're doing. So what I'm going to cover today, just to make sure everybody's we're on the same page, if you will, of what service-oriented architecture is, very high-level background, what remote procedure calls are, just so we're on the same terminology, what messaging means, what advanced messaging queuing protocol is, AMQP, if you're not familiar with that, and then Apache Thrift. And then we're going to bring all that together to do what it is as an application. So what is service-oriented architecture? It's an evolution of distributed computing. Most of you know and familiar with that from the internet and what that all means. It's a collection of loosely coupled independent system components. And what that means is all of these components should be able to operate independently without having to know what each other's doing. Each component should itself encapsulate some business logic, and the communication between those is typically using RPC. I don't know if that's me or somebody else. And one of my favorite quotes about SOA is right here what it says. If we build our systems as components, we can build and maintain them independently. SOA is a set of design patterns, effectively, that guide us in building and integrating these mini applications. So rather than sitting around and building a giant monolithic old school application, we can build these things as components. And then over time, as the system evolves and the needs of the business evolve, we can work on individual pieces. Where it becomes a little tricky, of course, is when you're talking about how do these things communicate with one another. And that's where messaging comes in. And as you'll see, it forms a nice abstraction layer between how you communicate between these components. So what are exactly service components? They should be single purpose. They should be encapsulated in terms of I shouldn't care how this service does its work. There should be a publicly defined contract that we both agree to. That's the protocol, if you will, where the API and the message types, the data that gets passed back and forth, is agreed upon. It should be context-free in terms of when I'm ready to pass something off to you to do as another service, you should be able to handle that on your own without needing anything extra from me. And of course, these things should be independently deployable and testable so that they can follow standard development practices of test-driven development and things like that. Communication between SOA components should just be, like, as I was saying, to support those things before. So they should be decoupled and have contracts that communicate between them to define the endpoints. The endpoints themselves should be decoupled in terms of I shouldn't have to know exactly where my message is going if I'm sending it. The underlying system can do some of that work for us through routing. They should support temporal decoupling in that I can be able to bring up and bring down services, and the system as a whole should continue to function, if you will. And the messaging between the components should be low latency and, of course, follow open standards. So, as I said, most SOA systems depend upon something called remote procedure calls, which are, of course, should be like function calls from the business logic's point of view. What typically happens in our RPC process is that you have a caller on one machine that is unaware of where the actual service is being fulfilled. So there's a representation of that code in the form of a stub that exists on the same machine. So the local business logic is calling that stub. The stub itself is going to marshal that data onto the network using the infrastructure that we're talking about later. And then that data is sent across, sent to a skeleton, which is the API interface, if you will, to the underlying framework, which then itself is going to call the business logic handling on the second machine. The functionality is going to occur, the data is going to be sent back following the same pathway. This is typically how most RPCs work. So messaging to the rescue, right? So messaging provides an easy way to communicate between distributed and loosely coupled components. It also allows with the framework for developers to focus on the business logic, whatever it is that they're trying to do in each service, and not on the underlying infrastructure. As long as the framework is the same then, and set out there and common across the infrastructure, it will do all the messaging for you. You can also move services around, and the messages will follow. The business logic itself doesn't have to care about things like that. It doesn't have to care about typically governance and how you do security, because hopefully your infrastructure is going to handle all that for it. This also allows for message formats can evolve over time with the business logic. So as you decide 3 months later you need to add a new parameter to a function in some business logic function, your message formats itself can change along with it. And the underlying infrastructure should be able to marshal that data and handle all the conversions as well in the versioning. Messaging is secure and scalable, and of course, it supports the RPC pattern amongst many others. So this is an example of an SOA architecture that I'm putting together with some others at PlayStation we're using for some hosting operations. And really, I'm not going to get into the details of that, but what I wanted to kind of showcase here is that the boxes in the light blue represent kind of services themselves that are operating independently as the loosely coupled components. And they all communicate with each other through the AMQP messaging broker. Now, of course, they're doing routing is happening inside that broker. So if service A is calling service B, it's passing that off to the broker, and the broker's doing that transfer. But it also allows for service-to-service messaging as well. So if I'm sitting on the GUI and I say I want to provision a new VM in the cloud, there's going to be a message that's going to come through the API gateway, down through the broker, maybe goes to the environment service to get some information from the database. Then it's going to go ahead and send a message over to the provisioning service. And we have a workflow service in there, which is, of course, delegating out all kinds of messages and doing orchestration. But the idea here is that all of these components work independently, and there's messaging going on between all of them. The other thing I like to point out is we have services over here, which, as you can see, are like Amazon, OpenStack, whatnot. And you can put a facade service following the facade design pattern just on top of anything externally, and then be able to invoke that using your internal messaging. It's an easy way to bring other functionality into the system over time as the needs of your business evolve. So what is AMQP? The Advanced Messaging Queuing Protocol. It's an open standard for doing messaging. Just a quick background here. The message in AMQP is very simple. It basically has a header and a body. The header contains, it's basically like a dictionary of name, value, pair keys. And it's used for contextual information to describe the message or whatnot. And it's also used for routing and other things that the broker itself can use. AMQP in particular, what I like about it is it's got a nice abstraction to it with the concept of the exchange of where you send messages to is kind of broken away from the actual queues by a binding mechanism. And so it allows for a lot of different and flexible configurations. And you could do a whole talk just on AMQP and the benefits of that as well. But at its very simple core, what you see is a publishing process sends or publishes a message to an exchange. And based upon the routing that's put into the message, the exchange will route it into the appropriate queue. And there's going to be a process sitting on the other end, hopefully, that is subscribed to that queue, and it's going to be receiving messages. And in a nutshell, that's basically how it works. It supports basic pub-sub messaging, RPC, and content-based writing. It's secure, reliable, and quote-unquote transactional in nature in terms of how the transfer of data happens. Because it's a binary wire protocol and it allows for that, it can interoperate across languages and platforms because ultimately it's just a bucket of bits. And it's up to the application how you want to use those bits. The centralized broker is also scalable, clusterable, and easy to configure, and of course, open standards and all that. So how does RPC over AMQP work? Well, it's quite simple. A client sends a message to an exchange, and it sends a routing key of what service, for example, that it wants to send to. On the other side, there's a service process running somewhere off in the cloud, let's say, we don't know where, and it's going to subscribe to the queue named OPQ here, for operation queue. So when the client sends a message, and if, let's say, assume it's a blocking call, it will also create its own queue for receiving responses and then sit and wait on block. Meanwhile, the service is just sitting there waiting to hear for messages. When the broker receives a message and is routed to that queue, it will notify the subscription process that there's a queue waiting, and it'll push the data out to it. The service can do its business logic or whatever, come up with a response, and then in the keys in the header section of the message, there's a reply to that's set to the response queue. So it'll send and publish the message back into the exchange. It'll get routed to the response queue, and then the broker will once again notify the client process that, hey, you have a response. And there's RPC. Of course, we build timeouts into all this stuff so that make sure that processes don't stick around. The other nice thing about it is there's automatic load balancing can be built in, but you can scale out by just having more subscribers sitting on your queue. And in that case, you'll have additional worker processes that'll handle the load as you need to. So I've used the term wire protocol. What does that mean? Well, if you're sitting around a bucket of bits and one side is written in Python and another side is written in Ruby, how are you going to know how to communicate? So the wire protocol is just that. It defines what data is being sent in what format. Typically, it's built around base data types, ints, strings, things like that, that are common across most programming languages. And so then it allows for me as a service or a client to communicate with another service, and I don't care what language it's written in. And this is where Thrift comes into play. So where Apache Thrift comes in is a project that was, I believe, it's an evolution of the Google protocol buffers, and it was started by the Facebook people and made into an open source project. It's got some benefits that it's language independent. It's a binary communication protocol. It allows you to, it comes with an interface definition language, which allows you to define those contracts that we talked about earlier between components. It also includes a code generator and a service framework, so it's a lot of stuff for free. If you assume that in a networking stack, you've got the raw transport of TCP or whatnot underneath it, where Apache Thrift comes in, it allows you to define a protocol, whether it be in binary, JSON, whatever. It's how that data is being structured and used across the underlying transport. It generates out a processor, which are those skeleton stubs that we talked about earlier. And then it provides for an ability to have a server mechanism built on top that can handle requests as they come in and be able to marshal the data, decrypt it, whatever is involved. And so just to cover, make sure we're still covering a lot of backgrounds here because we're built on the shoulders of giants, is the power of an interface definition language. And so this is the language that is typically, even though it's a language in itself, it's the programming language independent. It allows you to specify your APIs, message specification, validation. Of course, like I said, it's strongly typed because you have to know what data is being sent and what type it is. And this is what is used to generate those stubs and skeletons that I showed in that previous slide. And so here's a kind of like a high-level example of the tutorial. The Apache Thrift comes with a calculator tutorial, and so I've just kind of extended that with an AMQP transport to show us, to demo this. But what you can see here is that the service that is in the calculate service basically has a few operations, such as add, calculate, and I've added one for updating JSON because we found that the strongly typed transport becomes a little bit restricting. Sometimes it's nice to be able to send back flexible amounts of data, and of course JSON can be stringified, so it makes it real easy for things like that. But this is an example of an IDL where you specify the contract, if you will. So this service says, these operations are what I support, and these are the messages, if you will. The parameters and the return types become the messages of the operation that gets passed back and forth. And it can also throw exceptions, if you will. So Thrift supports the ability to define a exception, so when things get back, it can be sent back and itself becomes a message. You can also do non-blocking using like a one-way modifier, which says basically I'm going to fire the message off and then move on with my life. So just to make sure that we're all on the same page of what I'm going to demonstrate here in a minute, this is the Apache Thrift tutorial, if you will, kind of broken out. The boxes in blue are what the developer would write. So they would write the client side, how they're going to call the operation, what they're going to do with it. They would write that Thrift, like I showed you, the Thrift IDL, and then they would write the handler on the back end that would show the code that would handle the messages when they're actually being received. And then they'd write the surrounding server code to run it as a service. The boxes in yellow represent the generated code. So when you write the IDL, you'll see if you run the Apache Thrift tutorial itself, you generate, there's a compiler that comes with it. That's the biggest part of the installation is creating the compiler. And it will generate these stub files that are used to transfer the data around. And then the underlying pink are what would come normally with Thrift. Now, Thrift doesn't come with AMQP out of the box. This is something I wrote and I'm putting out there for anyone to use if they want. But the idea is that you can choose the binary protocols or JSON protocols or whatever that come with Thrift, and the AMQP transport just becomes yet another transport you can use along with anything else. But the idea behind the calculator tutorial is if I'm a client application and I'm going to call one of those operations like add or calculate or whatnot, I make those calls, the data flows down through the generated client code, gets put into the protocol, binarized up, into the message, put on the AMQP transport, which writes a message out to the service queue. The server is over there listening on the other end, receives the message, goes up the stack, comes up with the result, writes another message back out to the response queue, and then it's heard from the client in return. So now I want to look at some code here. So basically, this would be the Thrift IDL, if you will, as I kind of already showed. Let me get rid of this guy. And It's pretty much like I showed earlier. You have operations, and you're defining pretty much what the base types are, integer 32s, if you will. Or you can also do structures, which are nice. Example of a work structure, I think, is above. Yeah, so you can pass in, and this is their IDL is in a C format, of course, but you can do optional parameters as well. And that code you would normally just generate, and it would come up with, this would be generated code, which represents the calculator class. And you'll see in the way they're doing it, both sides of the skeletons and the stubs are generated. So on the client side, you'd have a class which is called, they're calling client, and it includes all the Thrift client-based stuff, but then you'll see for every operation, there's a send and receive function that comes along. So from the client's point of view, the developer client's point of view, you'd call the ping operation, for example. It internally then generates all the stuff to do a send receive of the ping, and then you get your data back. And there's one of those generated for every single operation. On the service side, there's the same thing. There's a process ping. Thrift does everything in terms of streams. So you've got a protocol for your incoming stream and your outgoing stream. So it kind of follows the same pattern. You read the arguments out of the stream, which is your message format. And it calls a handler, it calls the function in the handler, which will ultimately delegate out to the business logic that the developer is responsible for writing. And then it writes the results back that it receives onto the stream that gets sent back. And it includes all kinds of other built-in arguments, checking, validation, the fields, and all that stuff. And this is, like I said, all generated. Ultimately, the developer is responsible for writing the handler. So in the calculator handler, what do I do when I get a ping? What do I do when I receive an add? What do I do when I receive a calculate? And so what happens when that message comes into the generated code, ultimately it's going to be dispatched out through here. And then when you start up the service object itself, I have examples for doing sockets and HTTP in here as well. But effectively, all you're doing is starting the server, and then it just sits there and runs. And so what's happening under the surface in the AMQP code is when the server starts up, it's obviously making connections to the broker, but then it's going to come down here in the serve, and it's going to just basically hit this queue subscribe method, and it's going to just block. And only when a message is received from the broker, then is it's going to enter into this block and then proceed to do something. So in this case, if it can handle it, it's going to spawn up a new thread, and then from there it's going to, down here at the very bottom here, you can see it's going to delegate off to the processor, which was generated, the data that was received in the message. One thing that's interesting about, this is using the bunny gem, is that with AMQP is you cannot share you can share connections across threads, but you can't share channels. So the idea is that every time you spawn up a new thread, you create a new channel, and then you'll be fine. Once the process is done with its thing, we rewind the stream and pull the response back, and then we go ahead and write and publish out a message back onto the queue or onto the exchange, and it gets forwarded on to the client. So the same thing is happening on the other side. So the caller basically starts up, and it's going to just simply, this is where it gets real easy for a developer, is you're creating, if I can find it right here, you're creating the client, so the calculator client, and then you're just calling functions on it as if you're doing anything else, and you're passing your parameters, and you're going to get your results back. So the logic is very simple. You don't even know that messaging is happening under the covers. And that's pretty much what's going on with the client. And so you're dealing with it like normal function programming. On the AMQP side of things, what's happening is Thrift is ultimately bubbling all this down through this flush operation. And it's publishing a message out onto the exchange, setting the appropriate data to say what queue does it want to go to for the service in general. And then the reply to is what queue am I going to be listening to on the way back. And so then if it's a blocking call, it'll go ahead and do the same thing. It'll subscribe to that reply queue, and it'll just wait for the response to come back. Of course, we got timeout stuff built into all this so that things, threads and processes aren't stuck. And that's pretty much it. So what does that look like in real time is that I can just basically start up my Ruby server, or that Ruby calculator server, and I run the Ruby client. And so what you're seeing here is the operations are going off of simple calculator operations. And I have debugging on to help see this. But what you can see here is that a message gets received. These are the headers that come across in it. And the data is in binary form, so you can't really see it too well. But you can see that for ping, it's just doing basically a ping. For adding, it's taking a 1 and 1, and then its response will be, I guess I didn't print that part out. But that's pretty much what's going on there. And so if you want to do then load balancing, you'd basically just start up a second version of the software. And so running it again just means both of them are now handling messages. So it's pretty simple, straightforward. So one of the nice things about Thrift is that it does allow for handling versioning and compatibility issues. As your business logic evolves over time, because functionality evolves over time, your protocols need to evolve over time. And again, protocols here meaning the wired protocol. So Thrift supports the ability to add additional parameters to your messages, and it will handle situations where if you have older code still running, it'll still handle that data. Your old code obviously won't do anything with it, but then when you start up new code, it'll handle it as well. And if you follow some of the key things that they point out in their documentation, those are best practices. You can handle versioning pretty straightforward. And as I already pointed out, you can do server load balancing by having multiple worker processes that sit there and subscribe to the same queue. So as messages come onto the queue, it'll distribute them across workers, and you get some load balancing based in. This does require your services to be built stateless so that you can handle messages, but that's pretty much it. So I'm going to end up with just showing some references. If you download the slides, I'll put them up and post it somewhere. There's some interesting documentation online that kind of helps back up some of the things I've been talking about and can guide you through some of that. And that's pretty much it. If you have any questions, I'd be glad to take them. I did bring some PlayStation swag to encourage questions, so that's it then. That's it for me. Thanks.